Okay, this is lesson 2.4. These are graphs that enlighten and graphs that deceive. Now, it's important that we understand how to identify different parts of graphs. And so, the first graphs we're looking at here are scatter plots. Now, scatter plots just takes an XY coordinate and plots all the different points. For example, here we have waist circumference as your X value, and your Y value is arm circumference, okay? And it's seeing whether or not those correlate. Now, correlate means, do they affect one another? For example, a test at school. If the amount of time you study has a positive correlation to the grade you receive on your test. And so the grade you receive and the amount of time studying, they correlate. And you could graph that on a scatter plot and you'd see the correlation. Now, let's see. You could also maybe look at stores that are visited and the amount that you spend. Well, there'd definitely be a correspondence there, right? The more stores you go into, the more likely it is you're going to spend. Trust me, my wife does it to me all the time. All right. Now, correlation, it's important to note that correlation does not mean causation, okay? So just because two things correlate does not mean that one thing is causing the other thing. Just like a generic example I thought of is a cigarette smoked and the death rate in a small town. You could have a positive correlation between those two, but that doesn't mean that just because you're a smoker, you can't connect that cause. You can't say that because people are smoking, they're all dying. You know what I'm saying? There's lots of people that live to be 102 years old and they are avid smokers. And so, anyway, just because two things correlate does not mean there is causation there. You have to be able to think about it and analyze the data to be able to identify whether or not they actually do affect one another. It's obvious time studying for a test and the grade you get on the test are related. Now, the first graph you see here, this one has a positive correlation. You can see that it's bunched together going in a positive direction. As this one increases, so is this one increasing. So they're both increasing. That's a positive correlation. This graph over here, this graph has no correlation. The points are just everywhere, and so they have no correlation between each other. This is weight and pulse rate. There's no correlation between your weight and your pulse rate, okay? Although there does seem to be a positive correlation between waist circumference and arm circumference, although there may not be a true correlation there. That's something that you have to be able to think out. Now I'm going to show you my book real fast and show you the different types of correlation that you will identify. Two of them we already mentioned, but here we have positive correlation, which they basically go in a line up from left to right, and we have negative correlation, which is basically linear down from left to right, and we have no correlation. Now, positive correlation, as one thing increases, the other one does too, okay, and it forms basically a line. Negative correlation, as one thing increases, the other decreases. Now guys, you would think that negative correlation would be a bad thing, and in a lot of cases it is a bad thing. Like your profits are going down and you raise the prices of products, your profits are going down. That's a negative correlation. Now, negative correlation is not always bad, however, okay? Negative correlation, there can be good things about negative correlation. For example, increased security personnel and equipment and lower items being stolen from the store, so lower theft. That would be a negative correlation, but that would be a good correlation. The more security officers and equipment you buy, the less things are going to get stolen. And so it'll be a negative correlation. That's a good thing. Okay, so not all, just because we hear the word negative doesn't mean it's bad. All right, so that's scatter plots. Now, other things that we're looking at, there's clusters and gaps. Okay, this is looking at the weight of pennies for different years. There's no relationship here, right? You can see that pretty easily, and you can see the discrepancy going on here. There's a discrepancy in the different pennies that were observed here, okay? That's the reason why there's two different clusters, and it has nothing to do with the pennies themselves. Okay, time series graphs. Now this is the type of graph we're most used to, okay? These are quantitative, meaning numbers, and it's quantitative data collected at different points in time. So for example, your monthly bills. There's monthly, yearly. Anyway, we use this quite often. We look at things over a period of time, especially in business, since you guys are business majors. When you go into business, you are using time series graphs quite often. And you're looking at mostly you'll probably use it for profits, to see how your profits have increased, or you could even look at it for theft or whatever it might be, workplace injuries. Anyway, we use time series graphs quite a bit there, showing over a period of time how it's increased or decreased, okay? And so that's what this graph is showing. In 1980, things were about here. You can see that this steadily increased for a little while, and then it jumped up, and then it kind of petered out, and then right here we have really sporadic information going on here. So that means that this is dealing with the Dow Jones. That means the Dow Jones was jumping around a little bit here. So the Dow Jones was consistent here. Good time to be investing with the Dow Jones. And then it's still pretty good. And then great, but then all of a sudden it's dropping, right? So that's kind of sporadic. And so you have to be able to read a graph and interpret the graph and what's going on with those. That's a time series. Just to point out, these are in years right here. And this is the Dow Jones highs right here, okay? All right, next are dot plots. Let me get to where you can see those. Now dot plots is basically this. It's a line where you have all the values within your sequence of numbers. So this one goes they chose the range between 50 and 150, and all the points fall within that range. And then they also kept the scale consistent, 50, 60, 70, 80, 90, 100, right? And then above each place where the data was shown, this is dealing with IQs in this one, they placed a point above that point. So if it was 89, they put a point just before 90. So 89 would be right, well you can't see because my finger, right there, right? And so anyway, for any repeats, they stack it on top of each other. So this is just another way. It's not one of my favorite ways or anything, but it's just another way of analyzing data. You can see where the majority of the information is. You can see where it spikes a little bit, and that kind of stuff. And you can see it helps you interpret your data, and just another way of interpreting. Okay, time series obviously and scatter plots are two of the most common ones. Next is a stem and leaf plot. And I'm going to try and zoom in here on this one too a little bit to explain it. A stem and leaf plot just helps you kind of organize your data. And what it's doing here is it's taking the stem and then on the left side and then putting the leaf on the right side. So here's how we read this. This is 50 and the 0 means 50. And then this is 50 and 6, so 56. This would just be plain 6. There's no number there basically. 7 has 70, 72, 73, 74, 75, 76, 76, 76, 76, 76, right? And so forth. This is 111, 115, 115, and 118, right? So anyway, that's how you do a scatter plot. You put the stem, which is the first number, on the left side, and then its leaves on the right side, which is the remaining numbers. And it's a condensed way of writing all these numbers. I mean, I could write these numbers out in a long sequence of numbers and it would take up a whole page. But in this case, I could condense it down and I still know what all the numbers are fairly quickly. So that's a stem and leaf plot. Bar graphs. Let me zoom out. Here is a standard bar graph. This is a double bar graph. Anyway, bar graphs use bars with equal widths. Let me get it to stand. There we go. Use bars with equal widths to show frequency of data. Now you can easily identify here Look how much more the males have a median, the higher the income of the males compared to the females. So this is comparing male-female wages. All right, and you can easily see that through this bar graph. You'll also notice that this is not a histogram. There's a space between the bars. So if you wanted to make it a histogram, then you just connect the bars. It doesn't really look all that great when you're dealing with a double bar graph like this, but you could if you wanted to, okay? Anyway, by year, that graph is a bar graph showing the wages. And what they're doing is they took the year, they put the median income for males here and the median income for females here, and they just drew their bar up to those points. So that's how that works, pretty easily. There's scales over here, the income here, the year there. Okay, those are called scales, by the way. All right, let's see what we're on to. There's the Pareto chart. Pareto, these are bars that are arranged in descending order according to frequency to draw attention to more important categories. So in looking at this, if you can see, this says family slash partner. You can see that that's what you're drawing attention to, and it's in order, in decreasing order. So largest and then decreasing like that. Okay. So what contributes most to happiness? You can see obviously family is what makes people most happy, and then sports is last. Yeah, right. Everyone knows sports is first. No, I'm just kidding. All right, going on. Then there are pie charts. Now, pie chart, what it does is it takes a circle, right, just like you guys know, and it takes the percentage of each thing and just displays it within that circle. So this is 13% friends. So what contributes to happiness? 13%. That's only 13% of 360 degrees. You find that by multiplying 0.13 times 360 and find out that's 47 degrees. So you'd have a 47 degree slot there, okay? Or you could just pretty much estimate 13 degrees of, or 13% of the full circle. 13% of 100 is not very much. You can see family, family slash partner, that's a large majority, right? That was up above 60%, and so yeah, this is definitely 50% of that circle would be here. 60% looks pretty good to me, right? So anyway, pie charts are another way of displaying information, although pie charts are not the most effective way of demonstrating values or anything like that, because they don't really have an appropriate scale, okay? With the bar graph, we had a scale that showed us exactly what was going on. With the Pareto, we had a scale showing us exactly what was going on. There's no real scale going on here with this pie chart, okay? And so they're not usually favorable. Now, looking at graphs that deceive, what we're looking for is, let me get to where, a non-zero axis. So right here, you will see this graph is meant to deceive, the one on the left. So here's why this is a deceptive graph. Let me try and zoom in so you can see it even better, and we can discuss its aspects a little bit more. Look at this. It's comparing fuel consumption of these vehicles. Well, man, you'd think that the Toyota Camry this is miles per gallon up here, and this is each of the different vehicles. And so Toyota only gets just shy of 30, or about 31 miles per gallon. And if you look at these graphs, it looks like Honda is getting amazingly better gas mileage than Toyota, and still really much better than the Chevrolet. And so you're thinking, man, Honda is definitely the car for me. But if you look really close at the scale over here to the left, this scale starts at 30 and not at 0, which means this is not an accurate scale. This is a way that many companies show you graphs, and they're trying to deceive you into thinking that they are the best option for you, because they're leaving out the information, or they're making it appear like a much bigger gap than what it really is. Here is an accurate graph of what's really going on. Is there really that much difference between the different vehicles? Not at all. In fact, see, this one starts with 0, and the scale is consistent. It goes up 10, 20, 30, 40. Scales have to be consistent to not be deceiving. And now you can see that basically all these cars are almost getting the same gas mileage. So if you like the Toyota Camry, you're only getting about 5 miles per gallon less than the Honda Go with the Toyota Camry. You know what I mean? But this information right here does not help Honda sell their vehicle, and so they would give you this graph over there. Okay? All right. Pictograms also do not show accuracy. Okay? This is the number of passengers taking a flight in 1984 and the passenger in 2010. It's meant to show that it's doubled. Well, if you look at the size of those two planes, it actually looks like, you know, the one on the right is like 7 or 8 times larger than the one on the left. That means 7 or 8 times more people were flying in 2010 than in 1984. And so that's deceiving. The picture is not to scale, and so people can interpret that inaccurately, when really it's just double, okay, or something like that. So this more accurately displays the difference between the two in this graph here. Notice the scale on the left goes up by hundreds, starts with 0, so it gives them each a fair chance of showing what they really are. If this started at 300, you would think there was a huge gap between those two, because at 300, this would be a very small bar, and this would be a huge bar at 300. So you could be deceptive if you wanted to be, and that's what a lot of businesses do to get your business. So those are 2 ways in which graphs are deceptive. All right, that's it.